All right, this is the last class for this quantum mechanics course, and just to revise a little of the things that we have already talked about, we have talked about wave function, uh, which itself may not have any meaning, physical meaning associated with it, but the mod square of that gives you the probability density of finding a particle in certain region of space, and this psi or the wave function satisfies certain equation. This equation is called as a Schrodinger equation. We have from a plausibility argument we have derived that equation, and we have also understood that the solution of that equation gives us very important information about the system, which are its eigenvalues and the eigen functions. And the eigenvalues of this quantum mechanical problem, they have discrete or quantized eigenvalues, energy values, and these quantization has an unit of h cross associated with it. Okay, so it's not just not any kind of quantization; it's a quantization that has a scale which is set by the Planck's constant, and we have also derived for each of the problems that we have dealt with the corresponding wave functions, which we have called as the eigen functions. Okay, so but we have really dealt with only a few problems or a few classes of problems. One of them, or rather the first one, being the free particle in an infinite potential well, and we have seen that the wave functions are sine or sine or cosine depending on the kind of well that you have and whether they are, you're talking about the even functions or the odd functions, or corresponding to even n or odd n, and the energy eigenvalues for either of the cases, that goes as n square. So it really becomes more and more distant from the preceding one as n grows larger, and we have seen that the correspondence principle, that is the classical limit of this quantum problem, can be actually achieved when n goes to 0. Sorry, n goes to infinity, not n goes to 0. N goes to infinity, that is n being very large. Okay, and then we have also looked at operators in quantum mechanics, and these operators definitely have different properties than the operators that we know in algebra or in mathematics. These properties state that there are observables which are, or these operators, they may or may not commute with each other. Like for one example that we have seen, this and this px, or what we have written as simply p, assuming that we know we are doing it in one dimension. So this is equal to h I h cross, which means that it makes a difference that whether you first measure x, or then you measure px, or vice versa. So they don't commute, and this commutation, that is which is expressed by the square bracket, is not 0, it's equal to some value which is equal to I h cross, again set by the Planck's constant. Okay, each one of these operators are actually matrices. Okay, and these matrices obey certain equation which we have said as the eigenvalue equation, and we have introduced a little bit of linear algebra, not too much there, but at least the basic minimum of that these wave functions are actually a sort of vertical vector. It's a column vector with the entries as the, it's like the psi is like a column vector like this, and so we have written this as a ket psi, and the conjugate of that is actually is like a row vector. Okay, so the row vector, when it's getting multiplied with the column vector, you get a normalization which we have written as psi psi, which assuming that the psi is properly normalized, because that is a requirement of the quantum mechanical problem, because you need the probability to be 1 when you have searched everywhere in space, which means that you have integrated the probability density from minus infinity to plus infinity, then it should give you 1. Okay. So, there are then we have of course done the solution of Schrodinger equation in a number of types of potential, which are mostly simple cases where there are constant potential, either it's like a step or it's like a well, or we'll be seeing some more examples. I mean, we have seen such examples in the tutorial as well, and maybe some other examples you have seen in chemistry, where one has solved for the hydrogen atom, and the hydrogen atom we haven't done it because the hydrogen atom is actually a three-dimensional problem, and we have a problem where we have hydrogen atom is the simplest atom. So this is an atom, there is a a proton inside, and there is an electron here. So this is negatively charges for electrons, so let's write it as electron, and there's a proton there. So there is a attractive potential between that, which is given by minus E square over R, and so this R is not a X, R is the polar R, that is the magnitude of the vector R, which you write as R sine theta cos phi, R sine theta sine phi, and R cos theta. So it's a component of that vector, and again I'm pretty sure that the chemistry course also hasn't taught you how to exactly solve that Schrodinger equation for this potential, because the solution is somewhat complicated for a first year course before you know a lot of special functions mathematically, but that doesn't matter. I mean, you can actually, you have this psi is some a polynomial, or rather some function which is called as a log-ware polynomial, and it's multiplied by some r by a0. But what's more important is that, so and then there is another function which is a function of theta and phi, and so on, and the energy eigenvalues in that case is given by minus 13.6 by n square electron volt. This you might have known from your class 12th, where this formula is often written. So the electron in the 1s state, that's the lowest energy state, which n equal to 1, is minus 13.6 electron volt. And of course, because the energy is negative, it's the total energy of the electron. It is bound to the atom. You have to supply that much of energy in order to free the electron from the atom. Okay. So let me show a few things, not many of them, just a few things, and which we have skipped during the usual class. So you can consider them as individual problems. So prove that momentum is a Hermitian operator. So momentum operator is Hermitian. And the way you can show this is that, let's write a P, which is equal to the expectation value of P will be between two states which are eigenstates of the momentum, which is psi 2 and dx. So in general, the expectation value may contain two different states. We can also take it to be the same state. Okay, if you take this it to be the same states, that is psi 1 equal to psi 2, you get the diagonal elements of the matrix which the momentum represents. Okay, we just told you that these operators are all can be expressed in terms of matrices. So I write this a form of P which is minus IH cross del del x. So there is a minus infinity to plus infinity and then there is a psi 1 star minus. So this in that Dirac's notation it would mean psi 1 P psi 1 psi 2. So this is minus IH cross ddx or del del x you can write a psi 2 and a dx and you have to do this integral, and for doing the integral you can simply pull it in. So it's a d psi 2 dx psi 1 star and this IH cross can be taken out and written it here. So this is minus IH cross and then psi 1 star d psi 2 dx. If you do a by parts integration, this gives you minus IH cross psi 2 psi 1 star at infinity minus infinity and plus IH cross psi 2 d psi 1 dx star, okay, dx from minus infinity to plus infinity, okay. And now this term goes to 0 because the size will have to be square integrable. They cannot exist at infinity or at minus infinity because that would create a problem in the square integrability of the wave function, which leaves us only this term which can be written as actually it's like psi 2 p psi 1 and star, okay. So that's exactly what you need to prove that the momentum is a Hermitian operator. So this is exactly equal to this. So this is the definition of this operator Hermitian operators, okay. So let me do another an example which will derive the continuity equation. This has been mentioned but without either an explanation or what it means in terms of uh, expressions, etc. And so this is rho is what is called as now I can write it as both x and t mod square. So and uh, we'll see that we are getting an equation which is called as the equation of continuity, which is equal to del rho del t. So rho is a function of x and t, and plus a divergence of j, okay. So this j is called as the probability current density, and we'll derive the form for that. But to derive this equation, so we want to derive this equation, okay, and learn what is probability current density, because this is one of the important physical quantities associated with the wave function. So if we write down the Schrodinger equation, which is I h cross d psi dt, this is equal to minus h square over 2m d2 dx2 psi plus v psi. V could be a function of x and t, but usually we consider it to be only a function of x unless in some very specific situations such as electromagnetic wave. And so if I take the complex conjugate of this equation, which is minus IH cross d psi star dt, this is equal to minus h square over 2m d2 psi star dx. So this is dx square plus v psi star, where it is assumed that v equal to v star, that is the potential is real. Okay, So, this is our Schrodinger equation, and this is the complex conjugate of that equation. Okay. So, what we do is that we multiply this by psi star, okay, and so we multiply this by psi star, okay. So, I just write multiply here, and we multiply this by minus psi, okay. And if you do that, then what you get is, so this will be a psi star, so this will be, I am writing it here itself, it is a IH cross psi star d psi dt, and there is a psi star there, and then there is a V psi star, psi will give you a mod psi square, and if I multiply it by minus psi, then this minus sign will go away and I get a psi here, and then I get a psi here, and then I get a mod psi square again, okay. So, so you see that if I now take this thing and if I add both of them, what I get is the following. I get a IH cross psi star d psi dt plus a psi d psi star dt, and then there is a minus h square by 2m psi star d2 psi dx2 plus psi this will be, so when you multiply it by minus psi, this will be plus and this will be minus. So, this will be a minus sign here, and psi d2 psi star dx2 and this will cancel, okay. So, plus v psi square and this thing will cancel, and so this will be, so when I divide everything by IH cross, so I can divide everything by IH cross here, so 1 H cross will cancel and I get a minus 2 H cross by 2 mi. So, this can be written as a ddt of rho xt, because rho is equal to psi star psi, we have written that here, okay, and this is equal to minus h cross by 2 mi, and we can write this to be equal to a divergence of j, where j is equal to h cross by 2 mi and then psi star d psi dx minus psi d psi star dx. Okay. So, this is a current density, and if I take it to the other side, so this equation comes, and this is only I have taking it in one dimension. So, this divergence you can replace it by dj dx. Okay. So, in 3 dimension it is del rho del t equal to plus this divergence of j is equal to this, and in 1 dimension this will simply be equal to dj dx. So, this is the called as the continuity equation. This is one of the things that are important in quantum mechanics. Now, there are when two operators do not commute, just like x and p, you cannot measure them simultaneously. You cannot simultaneously measure them, and which is inbuilt into the the uncertainty principle, which says that the P and X measurement cannot be done with infinite precision. If you want to with infinite precision, you want to measure X, you have to give up measurement of P, and with a large precision, if you want to measure P, then you have to give up the precision in the measurement of X. So these are called as the non-commuting observables, and they also have quite important um, implications, that they cannot have simultaneous eigenfunctions. But however, if two operators commute, they can have simultaneous eigenfunctions, which means that their eigenfunctions are same. You can take them to be same. So one of the non-commuting observables you have seen as x and p. Let us see that there is an angular momentum operator which you have been exposed to in your classical mechanics course. It's no different in quantum mechanics, is accepting that it's an operator. So this L operator is just like classical definition, it's R cross P, but here P is not a continuous variable, P is minus IH cross del x or ddx. Okay. So, so Lx is equal to actually ypz minus zpy and so on. So, Ly is equal to zpx minus xpy, and Lz is zpx minus xpz. I'm sorry. Lz is equal to xpy minus ypx. Okay. Now, the components of this angular momentum operator, they don't commute. This is not equal to 0, which means that if you are trying to measure the components of the angular momentum operator with infinite precision or simultaneously, you cannot do that. Okay? You can only measure one at a time and cannot be done simultaneously. And if you want to prove this, then that's not difficult to prove. So this Lx is nothing but ypz minus zpy. So this is 1, and this is zpx minus xpz. So these are the terms. Now this will give rise to 4 terms which are like ypz and zpx. So the commutation of this and this, and now there will be minus ypz xpz minus zpy zpx and plus zpy xpz. Okay, I've taken any two components. You can take the Lx Lz, or you can take Ly, Ly Lz and so on. Okay, so you can check that this is these two terms is equal to 0. This term is equal to 0 and this term is equal to 0. You can write that and check because this will be like ypz xpz. Now pz will commute and xy do commute. So if you write it on the other side, that is not a problem. Same with this, because z is common, so it's a zpy and zpz, and zpy commutes, z and py commute, z and px commute. It's only x and px that don't commute. So these two are 0, and the first one is equal to, we can write it as ypx pz z plus ZPZ PYX, okay, and this is this will give rise to equal to minus IH cross YPX plus IH cross XPY. So this can be written as IH cross XPY minus YPX, and this is nothing but IH cross LZ. So what it says is that Lx Ly commutation is IH cross Lz. Let me write that here. Lx Ly commutation is IH cross Lz. Similarly, Ly Lz commutation is equal to IH cross Lx, and Lz Lx commutation is IH cross Ly. Okay. So if you combine all of them, then the L cross L is equal to IH cross L. That's the commutation relation of the angular momentum, because this is all, if you write this L cross L, which is equal to you know, the x component of L cross L is like Ly Lz minus Lz Ly, which is this one, and so on and so forth. Okay. So if you see component wise, then this is the equation, and that tells you that L cross L being not equal to 0 is a test that these are not like ordinary classical vectors or classical operators, for which if you are crossing it with the same vector, that would have given you 0. But here they are quantum mechanical operator and they don't vanish. Okay. All right. Let me tell you one maybe last thing. Let me just I'm trying to touch upon most of the areas that we have done. Let me take a case where we have, so this is that potential discontinuity problem, and so this is V equal to 0, and this is a height V1. So a particle which, you know, comes in from the maybe left, it sees that the potential is not 0 at the left of this x equal to 0, but it is equal to some V1, and then of course it becomes equal to V2 after x equal to 0, some V2. Okay. It could be V1 can be set to 0 also, it does not matter. So we are simply writing this as V of x equal to V1 minus infinity less than x less than 0. It's equal to V2 for x greater than 0, and let's have E to be somewhere here, that is E is greater than okay, so E could be either here, or it could be here, or it could be anywhere actually, it could be even. So let's take a special case that E is greater than both V1 and V2. More than solving this problem, I'm going to show you a very a nice method. It's a matrix method. You all know matrices. These are just 2 by 2 matrix for connecting the coefficients on left side of the region x equal to 0 to the right side. So we'll write down the solutions. So in region 1, so this is your region 1, say, and so your psi 1 is equal to a exponential I k1 x plus a b, or let's write it as a1 and a b1 exponential minus I k1 x, and in region 2 you can write it as psi 2 equal to some a2 exponential I k2 x plus b2 exponential minus I k2 x, where k1 is equal to 2m by h cross square e minus v1 square root and k2 equal to root over 2m by h cross square e minus v2. And you can take e to be anywhere, but I've just shown a particular case because this is not I'm not really trying to solve this equation, but I'm trying to show something else. So what are the boundary conditions? The boundary conditions are that psi 1 at 0 will be psi 2 at 0 at x equal to 0, and also that d psi d1 x at x equal to 0 is d psi d2 x at x equal to 0. Okay. So that gives us equations which are a1 plus b1 equal to a2 plus b2. That's the first equation. And the second equation is I k1 a1 minus b1 equal to I k2 a2 minus b2. All right. So we come back to this part of the board, and in order to solve this problem, that is finding the using this condition, find the reflection coefficient or transmission coefficient and things like that. Okay, so we can write this as a2 b2. These are the coefficients on the right side of the barrier. It's equal to 1 over 2 k2, and I write a matrix now which is k1 plus k2 and k2 minus k1, k2 minus k1 here again, and k1 plus k2 here, and this is connected to the a1 and b1. Okay, and let us call this as, you can divide it by k2 also. You can divide it, I mean you can call it as m k1 k2 a1 b1. Okay, so this matrix connects the coefficients between the right side and the left side, and if you want such a connection to exist for a1 b1 to a2 b2, you simply have to invert the matrix, and inverting a 2 by 2 matrix is very easy. You just swap the off diagonal elements and divide each one of the entries by the determinant. Okay, and this there are several properties of this matrix and so on, and this is one way that you can connect not only for one barrier, you can now do it for two barriers. Okay, so like there are two barriers like this. This is at x equal to say minus a, this x equal to a, this x equal to minus b, this x equal to b, and so on. Well, I mean you don't have to write it as, so it's a minus b, and this is x equal to a minus b, and this is x equal to a plus b, and so on. So you form regions which are like 1, 2, 3, 4, 5. Now you can equate coefficients of 1 and 2 by matching them at x equal to minus a. You can match coefficients of 2 and 3 by matching the coefficients of at x equal to a. by such a 2 by 2 matrix, and similarly for region 3, 4, 4, 5 and so on. So ultimately, you know, your coefficients of 1 can actually be connected to coefficients of the last region, okay, because this would simply involve, because this is connected to this and this is connected to this, so this is connected to this, it just involves multiplication of two by 2 matrices, which is very easy. And similarly, this is connected to this and this is connected to this, so this will be connected to this, and probably 4 or 5 matrices will come in between, and you can write down those matrices. This has a practical application, that if you are trying to know that what is the current through a random set of heterostructures in semiconductors, which you'll probably learn later, then what's the current through such an assembly of this potential wells or potential hills. And see, this can be absolutely random, that this it doesn't have to be same width as this one, or this doesn't have to be same height as this one. They can be of different heights, because these heights and energy will finally come through these K1, K2s, etc. Okay. So we have given you the first part of the course is about learning Lagrangian mechanics, which I'm sure that you have not been taught earlier, and that's a much more elegant way to know the exact path of the particles in going from x1 t1 to x2 t2. Okay, so some initial space-time position to final space-time position, and you've seen a very large number of such examples, and then you have applied the action being minimum across a path that actually the particle takes in going from one point to another. And then came relativity. Relativity taught you how to deal with systems that move at the speed of close to speed of light. Okay, it could be even 0.1 c, that's taken as comparable to the speed of light, and usual velocity addition or velocity subtraction formula will not work, and you have to fall back on the Lorentz transformation equations for the velocity, and the simultaneity of the events are quite important, as you've seen in 3 tutorials. And this you learn about the old quantum theory that has led to the that quantum mechanics to be developed, and in dealing with the quantum mechanics part, you have seen few types of potential for which you have solved the problem, Schrodinger's equation, and you have obtained the energy eigenvalues for that problem. Okay, so it's a good time to wind up the course, and hopefully you have learned a lot from this course, and that's what the idea of this is meant to be. All right.